Okay, you guys can see my screen, right?
Yes.
Perfect. Okay. So, this week we'll learn about generative adversarial networks, popularly called as GANs. And, GANs are widely used to make images, right? That images that don't exist are being made. I'm sure you guys have seen the examples, and I will show you a few examples. But, you should not, let this fool you into thinking, oh, this is just a nifty tool to make some images. It is a very, very deep and very, very important machine learning technique, because unlike other things which we have learned, those were discriminative models, right? That is, they are trying to learn, like conditional probability of y given x. GANs are generative model. That is, they're not trying to classify, they're trying to learn the joint distribution of x and y, right? That is probability of x comma y. And these kind of things, if done well, are really powerful, because now suddenly you have access to infinite amount of samples from your distribution, right? And you will see later on how, but it is harder to do, but you can, but you need to understand that GANs are just more than a tool to make images. GANs are a technique that will allow you to learn the distribution of your data source. If you had 1 million records, if you have no idea what they are, you can train a GAN on those records, and whatever that model is, that model has a lot more information about your data set than you would otherwise have. Just to recap, what was a neural network? Neural network is just composite of functions, right? And each of the function, could be linear, non-linear. There is some, weights involved. So there is some weighted multiplication. There is some sigmoid, softmax. But in general, there is some input and there's some output. Input could be same size as output, or output would be smaller. But overall, the whole process is that it's a sequence of functions. And more importantly, they are differentiable, because that is how we use it to compute gradients, which is used to update these weights, right? So these things we need to keep in mind, because that will come into play today. And second, what did we learn about the loss function, right? We learned that for classification you need a specific type of a loss function. And then what did we learn about the gradient optimization? That you need to take smaller steps to minimize the loss function. Right? Because, at some point you will start to realize that different types of AI or deep learning program, they're essentially same structure, but they have different objectives. And when it's objective, it just means loss function. Because what they are trained to do is different, even though they look very similar. And because they are trained to do different things, they are considered as different networks. Because the things I will teach you today, you have already seen all parts of it. But how they're optimized, how their loss function is designed, is what makes them a GAN. Right? So therefore, what in terms of components, I've already seen them, but we need to understand the special loss function that is that has been designed to train GANs. And the other thing to just to recap is we have learned about we have learned about CNNs, and we have learned about convolutions, right? Now, one thing we saw, with the convolutions was, this was really designed so that, progressively we can filter out some semantic information. And therefore, it also made sense that as you do more and more dimensions, more and more convolutions, the dimension of your feature, the space of your data reduces, right? So it starts from like, 200 by 200, eventually it goes down to like 5 by 5, then, then 1 by 1, and then you have that class. Why? Because, you will see later on that there is a different type of convolution where the goal is not to reduce the dimensionality, but to increase, go from smaller dimensions to larger, which, we haven't seen yet, but I will show you how that is used. And, we have seen, what does a filter do? Filter transform the image, right? Either filter can be hand designed like this, or it could be just the learned values that, the neural network, learns, to produce an output that is useful for the task. And we also quickly saw all these filters that these neurons are learning, right? The early layer filters. Okay, now let's look into this process, which I said is kind of like reverse of convolution. So that's why people call it deconvolution. Although technically it's not really a reverse of convolution. So technically deconvolution is the wrong word, but because some early papers wrote that word, so many people have overloaded the term deconvolution. What exactly we're going to learn is called as convolution transpose or transposed convolution, right? Instead of this figure, let's look at this animation. For the time being, let's only look at the left-hand side, right? This is what we saw before. This is what we are familiar with, right? The blue is your input. This, small gray, which is moving, is your filter, right? The kernel, and this green here is output, right? And as you can see here, the output size is smaller than the input size, right? Because if you had added one more layer of padding, probably it would have been all right. But because of the missing data, the output size is smaller, and that's fine because we mostly use this for classification, where we want to go down to smaller size, data. Convolution transpose is where you want to get a bigger sized output than the input, right? So what if your input was 3 by 3, right? This blue one, but if I wanted output to be larger, you imagine that between your points that there are these imaginary zeros, right? That is, in this case, the way we did padding only on the edges. Imagine doing padding around all around all the points, right? So in this case, there is like a padding of 1, right? So this is what is called as the dilation factor. Now, I mean, it is not implemented like this. This is only for you to visualize how it works. But the implementation need not be stored like this in a sparse form. But this is what is like you can think of it is happening. That now suddenly the input of this convolution is much larger than the original input, and now you do get output which is which could still be technically smaller than this intermediate input that you have created, but it's definitely bigger than the original input of 3 by 3, right? So convolution transpose is same as convolution, except it produces a bigger output size because it assumes missing values around every pixel, right? So here this is what we are showing here. This is the input. You get an output that looks bigger than the input, right? So you might be now asking, why would I ever want to get to a bigger output? Because when we studied when we studied classification or regression or object detection, what we learned that we want to go down from high dimension number of pixels to smaller one. But now with GANs, we're trying to make images, so we have to produce an output that is at least same size as input. And turns out the best way to do that is to do the similar structure as your autoencoder, which you learned in the first week. That is, you go from high dimension to lower, which is called as the bottleneck layer or bottleneck features, and then from smaller, then you go back to the larger one. So you are able to generate the image, but in the middle there is a smaller dimension. So when you have to go from smaller dimension to larger, you'll be using convolution transpose, right? Okay. And by the way, you should definitely check out this blog post, which clearly explains the whole deconvolution process. And there is one side effect of doing this deconvolution, that if you see the images generated, it has this checkerboard pattern right here. Let me show you right now. So these are the images generated by GANs, and if you watch them closely, you can see this very checkered board pattern, right? Very alternating dark and blue pattern. And if you see the blog, they do explain really well. But the reason it happens is because if you see, when you do this, moving window, depending on the stride size and depending on the kernel size, there will be few pixels that will be written multiple times, right? And because they will be written multiple times, they will have more value than the others. and that repeats, and that repetition has a pattern, and that pattern is determined the size of the stride. It leaves these kind of checkerboard patterns. Like for example, if I had a stride of 1 right here, let's say it will try to do it. So if I had a stride of 1, you'll see now that the pattern is slightly different. But if I had a kernel size which is even bigger, probably the pattern will be slightly different, right? So here you can see how the pattern would look like, and especially if you have 2 layers of this convolution transpose, depending on the stride and kernel size of each of them, you can see what kind of pattern you would get with a checkerboard. Now it is possible that if your stride is same as the kernel, that you might not get a pattern, but typically that is not the case, right? So I will encourage you to read this blog post to better understand. But if you see an output from GANs, and again, this is still, we are talking about very basic vanilla GANs. I will show you later on that people have definitely done a lot of improvements on top of GANs. But in general, when you use deconvolution to generate an image, you shouldn't be surprised if the generated image has this checkerboard patterns. Okay, I hope no questions so far. If any, please feel free to write them in the chat. I can see the chat even when I'm presenting. Okay, now just very quickly a difference between generative model and discriminative models. And I touched up on it at the start, but let's think of it again, right? If I had these set of points, and if these points belong to different classes, with discriminative model, all I'm interested is that given a point, I just need to know which side of this line the point falls, right? Whether it is on the left-hand side or on the right-hand side. Typically, we call it we call one of them as positive side, one of them as negative side. So it doesn't matter how far on the positive side. Now the goal is not, now it depends if you have SVM loss, at least this certain distance away from the, suppose certain distance away from the margin. But still, the overall idea is 2 blue points have no distinction as long as they both are blue points. It doesn't matter, right? We just need to be very accurate in being able to tell them apart, which side it is. Whereas with generative model, you need to know, each data point such that you have learned this function that is used to generate the data point, right? You can imagine whether it is natural images or it is just some set of random points. You can imagine that there is an oracle, there is a function that generates this data point, right? And instead of somebody giving you finite amount of data points, you just have access to this function, and you can run that function whenever you want and get as many points as you want. Now, of course, it means there are some assumptions baked in. That is, it's a continuous distribution so that you can sample infinite number of times. But similar ideas hold in a discrete distribution also, right? But you are doing more than just learning the boundary. You're trying to learn, is more than just trying to learn the discriminative boundary. You're trying to learn the boundary of all the data points of the same class, so that if you need more blue points, you can simply sample at them. So, in this case, if let's say my points were from a Gaussian for both blue and red, this means being able to learn the mean and the variance for blue and the red. Right? So if you have mean and the variance, then you have the generative model. You can generate more blue points. You can generate more red points. Now, for things like images, it's not going to be like a simple Gaussian distribution. It's going to be very complex, and the whole model, that is a generative model, is that function. That is, you treat that whole model as the process that can make more data points. So you simply sample more from this function, and you can get more and more images. So say suddenly the world ran out of cat images cat images, you can just go to the GAN and ask it to generate more, and it will generate more. And hopefully each time it generates unique, because just by chance, such image to exist will be almost 0. Okay, so this is the main difference between generative models and discriminative models, and will be GANs as a whole are generative models. But you will see later on that it has actually parts. There's a generative part and there's a discriminative part. Okay, now what would be the use case of generative models? With discriminative models, you can only do things like, tell me whether this is a puppy or a kitty, right? And then each of the item will be put in either this class or the other class. But what if you have images where you have mixture of both? Any discriminative model will not know that. Maybe it'll put close to the margin, but it'll just put one of the classes. A generative model could tell you that it is a mixture of two different distributions, and it can also tell you proportion, right? So you can do a lot more with generative model. In fact, you can do things like you can of course sample new data point. You can change certain features. I will show later on that how you can take a cat and take a different species of cat and do a species transfer, which is in ML word called a style transfer. And I can show you those things. But here this is generated real. So of course you can see this is very small images, so it's not easy to tell. But just from far, it looks like most of the images are equally good, if not great. So you can already tell that generated images already look very much like what we would expect a cat images to look. Now, before we dive more, so far one thing we have not seen is this idea that there is an adversarial system, right? And why this is important is because the GANs are designed to take advantage of adversarial system. So what is an adversarial system? Something where there are opposing forces, where doing something well in one means not doing well in the other, right? Because there's somebody who's trying to fight against you, and their objectives are different than yours, right? So you can think of this as also like an evolutionary algorithms, where you have this fitness and there's this nature, and the species might be deemed not to be fit, so that there's this adversarial thing that will either kill off the species, right? So even in genetic algorithms, people have trained genetic algorithms to search for awesome stuff. So you're used for search, and playing games where like if you're playing a game, then probably you're playing against the AI, and AI is trying to win against you, right? So it has its objectives are different than yours, right? Now, so in this way, now you might say, if there is no AI who's trying to play against me, and if this AI is trying to make images for me, shouldn't it just be helpful to me? Why should it be adversarial? And you will see later on that having an adversarial component allows you to balance the system, which if it is not balanced, it's hard to keep it stable and how to make useful results. Okay, now just a very briefly GAN. So GAN is this now it is considered as this whole class of method that is process to make new images, or it could even be audio, it can even be video, any modality of the data. But typically like the original GAN is just one paper which showed one particular method of training that allows you to make generate images. And this is what is called as the original GAN, which was I think published 2014 or something. Yeah. And now you can see there's so many different type of GANs. This is just some sample I just pulled randomly from a web page. I'm definitely sure there is a lot more of this. You don't have to try to know all of it. In fact, there's only one or two of it that definitely will have impact. And we'll talk a little bit about the cycle GAN today. We might talk a little bit about Wasserstein GAN. We might talk about stack GAN or info GAN, but you don't have to know all of this. Some of it is definitely repeated. Oh, actually, it's repeated right here when I copy paste it also. But most of them have try to tackle certain problems, or try to make it more efficient, or try to make it more stable. But at this point, there is more than hundreds of types of GANs, and there's plenty of papers that have worked in this space. Okay, so what is the objective, right? Objective in GAN is very simple. You start with a bunch of images, and at the end, you want to be able to make more images that look like your training examples, right? Now, in this case, you might look at this and you might say, hey, no, maybe it doesn't look like training examples. Maybe I can tell them apart. But if I had more examples like this, probably you won't be able to tell them apart, which is very meaningful. Like, for example, these are faces of people These are faces of people. There could be other varieties, other categories. If I only had, male population on left hand side and only female on the right hand side, then probably you could tell. But at least, if those things are mixed, you can't tell them apart, right? Now, so the goal is to generate images. And as you can see, we don't need any label, right? There's no need for why. There's no need for ground truth. So this is also kind of like an unsupervised technique. Now, technically, this is not really unsupervised because there will be some ground truth, there will be some why, right? So that you can compute the error and you can do you can compute the gradient. But that ground truth is easy to obtain. You don't need anything more than provided data, right? And that is why this is, almost like a self-supervised learning or, or unsupervised learning. Now, again, before we go, it's a good idea to take a look at some of these things. So there's this nice website called as This Person Does Not Exist. And each time you refresh, it makes this image where this person actually doesn't exist, right? This is all our, made up image of a person. It's so real, right? I mean, there's nothing in this image that looks, like, it looks more like robotic, or it's like machine made. It looks like somebody you might know, and looks very familiar. Very similar characteristics, well balanced. They don't mix gender traits. They don't mix, skin color. Skin color, for example, part of the skin being very different to another. Those mistakes don't happen. The hair, the hairline, the symmetry sometimes is well preserved. So you can definitely play with this, but there's also this another website called as This X Doesn't Exist, because people took this idea and applied to many different things, where now you just make cats, you just make some animes, you just make some emojis, questions, answers. So all these generative models, we can simply sample. In fact, you don't even have to make your own meme. It will make a meme for you. Each time you refresh, it's something new, right? And probably it might use an existing template, but it'll make something new. So you can definitely, play with this. So it makes, new chemicals. Now these chemicals, doesn't exist. Now we might not even know how to synthesize this, but it could be the new revolutionary drug. And there are a lot of companies that actually produce new compounds like this and then test it in the lab to see if this will work as a drug or not. And if it works, then it will go to clinical trials. And I think a couple of drugs right now are in clinical trials that were completely designed de novo by using machine learning algorithms. Okay, but there's something called as uncanny valley, and I hope you guys will remember this, because oftentimes when you start generating these images, especially like faces, it initially it looks very weird, like you don't care about it. It starts looking good, but then still it is but then suddenly it drops to a place where it looks very weird. It looks very alien like. Instead of becoming cartoon, it becomes alien because it is closer to human, but yet it has some faults that looks weird. Like, for example, in this eye here I generated from this one, and it failed. And typically eyes are considered to be harder because there's a lot of things, a lot of small parts, and humans are really good at looking at eye and being able to identify all these individual parts. So if you start generating your images and if you are not using latest state-of-the-art techniques, it's possible that you will generate these images that will look very weird. But then once you start throwing new techniques, they will overcome that. I'm not saying that current GANs are at a place where for any kind of data set they can make very realistic images, but for many of the cases they do work really well, and they are close to passing the Turing test where people cannot tell apart. But I think for now, maybe people can tell apart. But if you really had to find some technique to tell whether or not it is generated by a GAN or it's a real, just look at the eyes carefully. Oftentimes, eyes will tell you whether it's real or not. Okay, now, what I said, the goal is to make images that are, that look like this data set, or what you call as plausible examples, right? Plausible samples. How do we know, right? Even when we looked at these set of images, probably, like we said, oh yeah, these are faces, okay, maybe they are same data set, right? But if I were to, give you another set of faces, but if something is off, you as a human, you'll be able to look at it and you'll be able to catch it. But for computers, that something off is not defined, right? You need to be able to define why it is off, how it is off. This is just a sequence of numbers. This is a sequence of numbers. How are they different, right? And as we know, as you go higher and higher dimension, that all of your data points, they are, within the unit, within the unit sphere. Distances are all meaningless. So there is very little you can do at a raw image space, where if I give you two images and if I were to ask you are they same or not, other than to literally comparing every pixel, where yes, these two are literally the same image, that's easy to do. But oh, does this image look like something that could be part of this set? And that is something machines cannot do, because they don't know what it means to be a set of images, right? So these kind of things are really hard to do. So the hardest challenge in trying to generate data points is being able to tell if these data points look like they could be part of the training set, because there's no real test other than like human intelligence that can tell, right? Because ultimately, if our goal is to fool some human into believing that these images are same as real, then only human can do that test, because by definition it is a human test. But you want a proxy, you want some machine loss function that starts mimicking that, right? And this is where people had this idea about generative models for a long time. Autoencoders were in place, denoising autoencoders were in place, but they never scaled. They never scaled to more than like 10 by 10, because as you start increasing the dimensions, things become very hard, right? And this is where you have this curse of dimensionality that comes into play. So obviously, the reason we are talking about this topic here is a solution to all tough problems in machine learning is deep learning. And again, I'm being a little bit sarcastic there, but in this case, thankfully, yes, solution was deep learning. That is when you have a lot of data and you have efficient way to train it. You don't have to do a lot of creative thinking. You can simply throw the data. But there, of course, you have to sometimes be very clever. And here the clever is how this whole thing is structured, right? Like I said earlier, the parts of this you have definitely seen it, but how it works in tandem, that is what makes it again, right? So obviously, when we're looking at the images, you want to be able to tell whether they're real or fake, right? So question is, if we had a bunch of real images and if we had a bunch of fake images, we can train a classifier, right? I can tell a classifier, okay, just look at these images, call it real. Look at images like this, call it fake. But the thing is, I'm only giving you a bunch of real images, right? I'm not giving you a bunch of fake images, right? So you can't train a classifier to tell whether or not image is real or fake, because you only have examples from one class. Now, I mean, there are ways around this. There is this thing called as one class, classifier. There's also one class SVM, where you can just imagine that every all data points is in some space, and further away you go from from that space, more likely that it is a fake point, right? So you have this continuous thing that everything that is very, very far away from the mean, it's more fake. So you can do that, right? Or you can say, what if I make fake images? Because if you are using computer to make some images, by definition, they are fake, right? Because then they're not real. So you can do this. Now, if you do that, problem is, what if we're starting from this noise, right? This noise is definitely not a cat, right? So if I have a bunch of noise like this and a bunch of a cat, will I be able to train? No, because this noise is not really helpful in telling the model why this is not a cat. Yes, there's nothing here about cat, but the signal is really dispersed everywhere, right? It'll be nice, it'll be more meaningful to give the network smoother ramp, like a little bit more signal than just saying, oh, this is a noise, this is not a cat. We need something that has some features, but some features missing, so that we can tell, or some features extra that we can tell this is not a cat, right? So this is the idea, right? So overall, this is how a GAN looks like. So you have real images, which I give you, right? You just take one of it. And you have this, generator. Generator is, again, I will come to how to make a generator, but this is where, convolution transpose comes into play, where you just throw in a random noise like this, right? But your generator, has the ability to, change that and make something, right? And again, I don't know what it is making, but what I'm saying is it is able to take in a noise like this and transform this to some intermediate representation, right? So now I have either a real image or this intermediate version or transformed noise, right? So, let me just call it as a fake image. And now I have real and fake, and the label for the fake image is fake. And I have a discriminator. So now I can just train the discriminator like a normal classifier, two-class classifier, where it is either the images are real or it is fake, right? So I have the gradient and I will wrap over the gradient. It's all perfect, right? So the discriminator part is very simple. It just takes two images. I mean, it like doesn't have to take both at the same time. It just takes a bunch of images. Each of them have label, and we're just trying to improve the discriminator all the time. It's only ground truth, so each image has real or fake, and just trying to improve. Now, what is the generator, right? Like I said, generator takes in a bunch of noise, makes something, that is like a fake image. And this is where, like the $1 million leap of faith, like the $1 million idea for GAN model came. Where like generator is trying to convert this random noise into something that looks like a real world image, right? Now, so I mean, that was the whole goal of the GANs, right? To make images that look real. But the way we do here is, so remember the discriminator is a neural network, so it has a loss function, right? Its loss function is to make this classifier as accurate as possible. Now, generator is also a neural network. Think of it as an MLP. It also has its own loss function. Here it is not shown. Here only the loss function or discriminator is shown, but it will have its own separate line for loss function. And generator is trained to make these sample images be as close to real images, like pixel to pixel, point to point. That is, or in other ways, if discriminator is successfully able to tell them apart, generator has failed, right? That is the goal of the generator, is to fool the discriminator. And goal of the discriminator is to be really good that it doesn't get fooled by generator. This is where this adversarial nature comes into play. This is where, they have this two player, right? Both of them trying to play against each other. So generator, if discriminator is successful, it gets an error that is, like a wrong class. If discriminator is unsuccessful in able to tell them apart, then it gets no gradient because that is a success, right? That's like a true class. In my case, the true class is discriminator is successful. So if it has failed, and in this case, negative class is when discriminator has been successful, right? So if discriminator is very good, generator has a lot to learn, and if generator is very good, then discriminator has a lot to learn, right? What does it mean if I say, oh, in this GAN, the generator is really good? It means the generative images are so good that the discriminator is never able to tell them apart. That is the probability, or if for each class being real or fake is close to 0.5, right? It means discriminator is not good, right? Now, immediately you should be able to see a problem here, right? A problem is if I have a terrible discriminator, right? Or discriminator that simply flips a coin, whether the image is real or fake, right? So even if I give noise like this directly without any transformation, if my discriminator is terrible, half of the time it might say, oh, this is a cat. And then you can see then if discriminator is always failing, generator cannot improve. So now the question is, how do you improve the discriminator if generator is so good? And vice versa, what if discriminator is so good that generator is never able to learn, right? Because it is always making noise, and it is stuck making noise because it is never getting the other side of the gradient, right? It doesn't know what it's doing right? So this is where these kind of real world problems about GAN comes in. We'll touch about the problems later on, but there's this problem whenever you have two loss functions, both of them are antagonistic, but then both of them need to be improved from zero. It's very hard to sync them, right? Otherwise, it is likely that you will fall into what is called as a mode collapse. That is, the generator is able to produce one really good example, and discriminator is not able to tell apart, And generator has learned that, so it doesn't matter what noise you provide, it just makes this one good image of cat, and each time it's going to seize that. Remember, there is no label, there's no identity. Each time the discriminator just has to tell whether it's a real cat or not. So if a generator can make one cat that's really good, discriminator will never improve, right? And generator will never improve because generator can only do one image. So this is what is called as a mode collapse. And these are the kind of things that can happen, and I will show you how to overcome them. Okay, so now let's let's dive deep and see what are these components, right? What is a discriminator? Like I said, discriminator could literally be a replacement of your ResNet 50. Now, in this case, like ResNet 50 was designed for ImageNet with 1,000 classes. This case, doesn't matter what images you take, what data set you take, number of classes will always be 2, right? Real or fake. That's the class label. So it turns out you don't need very advanced, very complicated discriminator. A small VGG like thing or a small ResNet 34, ResNet 18 will do. So simple ConNet classifier that we saw in lecture 2. Right? Now, like I said, it takes in images and tells them real or fake. Now, this is where the interesting part comes. What does a generator look like? Generator, like I said, will go from some noise to some image. Now, it turns down in this case, the dimensions of the noise is arbitrarily picked to be a smaller size than the dimensions of the image that you're trying to make, right? If I'm trying to make 64 by 64 by 3, how much is that? Okay, who was really good at math? 64 by 3 is 12,288, right? So the dimensions of my image is 12,000, whereas my input dimension is 100. Because remember, these are just 100 random points. You don't need more randomness. 100 dimension random point is very random. So I want to go from 100 dimension to 12,000. It means I have to increase the dimensionality of the data, not reduce. If you're a classifier, this whole image will be flipped, right? It'll go from image to a few points. But in this case, it looks reversed. It's almost as if a 100-way classifier has been flipped from back to front, right? So the final layer, then there's a conv layer, then there's another conv layer and the conv layer. But in all of this case, it is a convolution transpose. So the output generated is bigger in spatial dimension, and in the number of channels is determined by number of filters. So you can start with a really large number of channels and then slowly reduce it to 3. And you can just, now you might say, oh, how do I know which one is red, which one is green, which one is blue? We don't care. We let the model figure it out, right? If model really picked the wrong channel to be red, discriminator will be able to catch it very quickly, and generator will have to learn to undo that if it wants to improve, right? So remember, it doesn't matter what mistakes you do, the model will just learn to make this. Remember, this is still a tensor, 64 by 64 by 3. But this tensor will start to look like an image, because that is the whole purpose of generator. Take in a random noise, and then use this as your input, use the convolution transpose, make it bigger until it's the same size as the real image. And this is what is the purpose of generator. Okay. So now this, this is now this noise would be now considered as a latent vector, because this is the idea is that this vector is much smaller dimension, right? So it captures encodes that information at a much lower space, and from this space you are able to generate images, right? So definitely it must be storing something very, very useful. Now it is technically we are sampling random noise, right? We are sampling from a random distribution, but that is just our shortcut, right? Probably there is some other distribution, but we can assume that what if I have two latent space in two different vectors? What happens to all the points in between? And it turns out there is a meaning for that. So for now, you can just assume this as what you call as latent vector, but later on you can see how this vector is closely tied to the characteristics of the image. Even though it's randomly sampled, the values in this have meaning, because those values determine what image you get. Of course, it is also determined by the network that you have learned, but the network is always going to be fixed, right? Once you've learned it, it's the same fixed network, the same weights. But if you have slightly different inputs, it might produce slightly different outputs. It means it is sensitive to the input. It means the values of the input, which are only 100 dimension, have the capability to change the output that is 12,000 dimensions, right? So it is definitely a latent vector. Latent vector means it is, some smaller dimension, vector which controls semantics, which has a much higher signal to noise reduction ratio. Okay, now what does the loss function look like for discriminator? Again, it's a classifier, two-class, binary cross entropy, right? Perfect, simple. But what about generator? This is where it gets complicated, right? Because I said generators would get a penalty if the image doesn't look like real. So you can do, or if discriminator is successful. So you will see how to play with the discriminator's output to use as a loss in generator, right? Okay, let's first get a few things place. Let X be the sample, right? I just means ith sample. There is I1 to IM some number of samples. Z are your vectors. These are the random data points that are sampled. But this could be lower dimension, same, doesn't matter. We start with Z, and then and then you start with X, right? So these two are basically your inputs. D is your whole discriminator, right? So discriminator basically discriminator takes one thing and it tells you whether it is real or fake, right? So if it is discriminator, we can so it will either take in a real image, so that is Xi, or it will take a generated image or a fake image. How are we getting fake image? Fake image is the output of the generator. So let's call the whole generator as G. So what is G taking? G takes in the latent vector, also called as a seed or the random number, produces a fake image, and then that fake image is given to discriminator, right? So what do we want for the discriminator, right? That is, if it is doing perfect job, right? We want the loss to be 0, right? When will this whole value be 0, right? Here there is a log of something. So when this is 0, right? When D of this is 0, this thing is 0, right? And this thing is 0 when there is 1 here, right? So when this thing is 1, right? So this thing is 1, it means if it is perfectly able, so far, if it is a if it is a correct image, we don't want any loss, right? If it is, and if it is incorrectly classified, we want some loss. So you can see here, this is higher the probability for a real image to be fake, more the loss will be, right? Because if this number is lower, so high probability means high probability for real means high probability for fake means lower probability for real, right? So this will be a low number, right? And this will be a higher number, so this loss will be high, right? So we want this loss to be a log of 1, right? So we want this to be closer to 1, and this to be closer to 0, right? So when you train like this, so when you try to minimize this whole thing, you are minimizing the loss for the discriminator. Now, and remember, what is the output of D of Xi? It's just a number between 0 to 1. Right? It's a probability for that image to be real. Right? So in that way, if it is perfectly real, we have this 0 loss. And this is still relatively straightforward, given we have already seen discriminative models. We have already seen a classifier. Right now, the trick is, what would a loss for a generator look like, right? So if the discriminator is incorrect, right, we want the loss for generator to be lower. If the loss for the discriminator is higher, right, we want and if the loss for the generator is lower, sorry, for discriminator is lower, we want this to be higher, right? Because we want this to be antagonistic. So let's see what this does, right? If you simply have this. So if it is a real image, so in this case, we are producing, so generator there's no real image, it's only a synthetic image, right? So we are producing a synthetic image, right, from G of, and now we are giving it to discriminator. If it is higher value, right, it means this value is closer to this whole thing is closer to 1, and this value is closer to 0, right? It means it has the image that we generated with high probability, it thinks it is real, it means it is a success for the generator, right? But if this value is small, right, and then you will have a larger loss, right? So in this way, these two loss will come into play. So discriminator is trying to maximize this, and the generator is trying to minimize this. Or you can simply change the sign. There's no minus here. You can just actually add the minus here, which I almost always in this minus. So you're minimizing both of them, because I think typically when you write your optimizer, like it gets confusing if you want to minimize something, maximize something. Almost always by default they minimize. So simply add a minus here, and then you minimize all of this. And in case of generator, we're trying to minimize all of this. Okay. Now, it turns out, this is great in theory, but in practice, it's tricky, because how do you remember this whole network is like this, right? They are tied, right? So if you found if you did a forward pass, and if you found out that discriminator was not successful in changing, in fooling the generator, and if you use that to change the weights of discriminator, it would be successful in fooling the generator, right? So you'll never get to a step where generator also gets to learn the mistake. So this is why, instead of jointly training GANs, the way to train them is to update them one at a time, right? So you do forward pass with generator without any updating any weights of generator. Now you do forward pass of discriminator with the real image, and then you update then you update the weights independently, and then you do one pass of this. So typically how people will do is you run generator once, then you run discriminator once, then you generator once. Sometimes it turns out you need a kickstarter, so people will run generator a few steps before they let the discriminator kick in, but you want to do this. Second, if you're using things like batch normalization, you don't want to mix these things in a single batch, right? Because otherwise these values will be shared. The batch parameters will be shared across real and fake, and the model, this is what it called as a label leak. Model will be able to use that to basically learn, because the distribution of real and fake images initially will be very different. So the batch parameters will very quickly learn to adapt them, and these things will not learn. So if you do have a batch, you are only passing real images, or you're only passing generated images, not mix of this. Yeah. Okay. Let's because I know this was too many stuff. Let's just look, like summarize the process again, right? So what is the step number one? Step one is we need some sample of real images, and we need to be able to draw some random values, right? So draw samples from Z, some random distribution, and compute GZ. So GZ is your fake image, that generated image. Then run it through a discriminator, right? Which tells you how good the fake image is. Compute the gradients of G with respect to the loss function. Remember, the whole thing has to be differentiable. That is another important thing, because for a long time, people didn't realize that once you have the differential network, there are a lot of cool stuff that you can do, right? And now that you have compute the gradients of G, you update the parameters of G, right? But don't update the parameters of D, right? You don't want that parameters to influence D. You need to be able to freeze the D when you update G. Now, see, now that you have made a fake image, get a real image, give it to the discriminator, see, find its loss, and then adjust the parameters of discriminator. So you have done one step. Now you repeat this again. Now you might ask, wait a second. At least when we did cross entropy or mean square error loss, we know that as the loss goes lower and lower, it means then the network is improving, and then at some point loss will stop improving, and then you can use early stopping to stop the training process. In this case, you can see how the loss function will fluctuate, right? It is not about low or high. It's about if generator is really good, for time being it will not improve, but the discriminator will improve because it has to overcome a harder generator, and then there will be improvement in the discriminator loss, but not in the generator. And then similarly, generator might start learning once discriminator is much better. But at no point, so they are like seesawing, right? At no point in time, you can look at the loss and say, okay, this is a good network. Because if the loss of discriminator is higher than generator, it just means one is better than the other. It could be at an early stage of the network where discriminator is really bad at identifying stuff, and generator is really bad at generating stuff, right? So their loss looks to have, be very similar, or both of them could be really well, right? So in both the things, the absolute values could be very similar. So don't get fooled when training GANs by trying to watch your loss function. But the things like Wasserstein GAN are designed to improve upon this, where they use a different kind of loss function, like instead of using this min-max loss. And in those cases, the absolute value does make sense, and therefore the lower the value, the better it is. But I mean, we may not have time to discuss Wasserstein GAN, but if you're interested, you should look it up. It is slightly heavier on the mathematics to understand why that loss function makes sense. But if you're interested, you should definitely check that out. Okay. Now, what does the training process look like, right? As you can see, the training process, sometimes you will see, you will get stuck within 2 points, right? Because it'll improve, it'll make good results, like start to make good images, and then suddenly it will come back to make bad images. And you can see how this can happen, right? Because the quality of the generator really depends on the quality of the discriminator, right? So at some point, discriminator, if discriminator is not able to improve, then the network will, will not get the right gradient, so it will start to go bad. And then again, if, like once it is bad enough, then it'll get good gradients from the discriminator and it'll start improving. But once discriminator again stops giving good gradients, it'll stop improving. So sometimes you will seesaw in these kind of values. And by the way, this image is from really old, like one of the oldest GAN paper called as DC GAN. It's here, and things have improved much better. But while you're trying to study, it's always good to study with the basic implementations. Otherwise, it gets too complicated to understand what is going on. Okay, now what about this Z, right? I told you that each time you have to make a new example, you just sample multiple points, like you sample a value in Z, so say you have trained your GAN, right? Once you've done the training, there is the, these parts are not there. You only run the generator, right? So you take Z, you pass the generator, now you've got an image. Now, what if I take another Z and then I take all the intermediate values, or essentially what if I interpolate them, right? So if my image from Z1 looks like this, and if my image from Z2 looks like this, right? Now, it turns out, and this is by coincidence, although some people have good theory to explain it, but it is mostly coincidence and retrospective analysis, where if we take values of Z that is in between, like interpolation in between, the outputs they make, they also kind of look like in between, right? So it almost looks like this image, like if you're trying to morph this image into this image, whatever it would look like in the middle, you get those intermediate steps. So here, I'm only showing you like 6 sample points. If you do 100 sample points, it'll do a very slow graduation, slow gradual morphing, like you'll have 100 intermediate points. So in GAN world, this is what is called as walking on the latent space, right, or interpolating on the latent space. That is, we are able to change. You are able to interpolate on the latent space and able to get the images that are, like all of these are kind of digits, right? Like none of this, probably maybe this one image is unrealistic, but typically the idea is that it does produce all the images that are realistic. That is, they all look, remember, what is the goal of GAN? GAN is, doesn't matter what the input image is, it has mapped this, random number to a space where all the points are plausible images of this data type. So in the case of MNIST, it is supposed to make digits. Now it's not perfect, but somebody could say this is like a 5, these are all 5, this is all ones, like the poorly written 1s and 5, but these are all naturally occurring numbers, right? So this allowed people to hypothesize that these images lie on the manifolds, right? So when I say manifold, it just means like a surface, like a texture on a high dimension space. That is, it is possible to walk from one point on the manifold to another point. So imagine there's a sphere here. Let me see if I can pull an image of a manifold and I can try to draw that. That's the problem. It's a car part, right? So let's say, now this is not a good image, but let's say this is a manifold of natural images, right? So it means all the natural images lie on the surface. They are not detached. They are not part of different groupings. It means if you are at one point here, oops, this is not what I wanted. Come on, over here we go. So say you are at this one point, there is a continuous path from this point to any other point on the manifold. It means all the points are plausible images, right? That is, the space of plausible images is not discrete. Now, again, this is a hypothesis. There is some, technical ways of showing this might be true, this might be wrong, but it turns out that is what you can do. And you'll see how people have taken this idea and gone to the extreme to do a lot of image manipulation, including deep fakes. So, and I will show you how good they are. So now what happens if we are able to interpolate, right? That is, if I take two, so if I take, two different sample, two different images, now, by the way, these images are small, but as you can see, for a long time, GANs were stuck on images like that are very small. So new data sets were generated that are natural or like challenging than MNIST, but they are still spatially very small. So this is called as LSUM. I think it's called as LSUM, bedrooms and hotels and rooms, that sort of stuff it has. So this is a bedroom, right? So if you go from, like, for example, between this, so there's a window here, there is, like a covered window here. So if I simply give these two images, and if I try to interpolate in between, you can see all the images in between are plausible bedrooms, but slowly they go from fully open window to to completely opaque window. Or if I go from a window lighted room to a no window lamp lighted room, slowly the transformation happens. Now, I'm not saying this transformation always happens in the way you and we would do it in our mind, but for new network, this is the working on the manifold to go from one image to another image, right? Because all the images in between are also plausible real images. Okay. Now it means you can also do some interesting stuff, right? Because we have the z vectors, right? So basically here operations are actually done on z, but you get this output. So if you take a smiling woman, if you subtract a neutral woman, and if you add a neutral man, you are able to get a smiling man, right? It means somehow it was able to subtract the feature that corresponds to woman, right? Therefore, now it is gender neutral. And so if initially this included two features, smiling and woman, now that you have subtracted woman, only feature that is left is smiling. And therefore, when you add these two vectors, and if you generate a new image from this added two vector, turns out the generated image has the combination of these two features. Again, this is a purely coincidental, but again, it's going to be surprising a lot, but it's definitely very cool and very neat. Although not much has been done with these kind of mathematics, but tells you one thing, that it is possible to disentangle these semantic features from the image, right? There's a concept called as smiling, and the networks and the models can learn what it means to be smiling. Now, it might not be many ways we can use it, but there are ways. And but you can see these images are, these are from 2015 paper, right? So now things are definitely improved more than this. Okay. Similarly, here, if you go from female to male, as you can see with many different images, it does this transformation. And it's not always clear what it is doing, right? Is it going from looking left-hand side to looking right-hand side, or is it changing the gender? We don't know which of the semantic feature is most salient here, and which is being changed across these images. But you can do all sort of stuff if you play with the data. So if you play with the latent vector and the generated images. Okay. And this is some of the pitfalls I told you about, right? That is, what if it is able to make one good image, right? Then, the generator has no incentive to learn more good images, because each time the generator gets a penalty if the image it generated looks fake. So of course, it is much harder to be able to generate a lot of fake images. It's so much easier to just memorize one really good image, and just regardless of what the input random number you provide, it always, just throws away the random number, gives you the same output. That can happen. It happens sometimes, and that's what is called as, mode collapse. And if that happens, there are other ways to tackle it, but the best way is to change the loss function. Instead of doing this min max, which is unstable, use persistent distance and other newer loss functions where, these things are less likely to happen. Okay, let's look at more actually what is going on, right? Remember, z is your random number, right? The latent vector. Here x is the image space, right? The manifold. Now, in this case, the green line is the output, right? Of the generator. The dotted lines are the real data, right? And the black dotted lines, because so again, so remember, black dotted line is the true distribution that we're trying to learn via this generative model. So green is our approximation of true distribution, right? And blue dotted line is what does the loss of a discriminator look like, right? So you can see here, when the network has perfectly learned the distribution, right? That is, green overlaps the true data. It means each of data is so good that impossible to tell whether it is real or fake. So the discriminator has a fixed, it is at 0.5, one straight line. For each of the data point, it cannot tell whether it's real or fake. It's all of these data points, they all look real to the network, right? And they should look real because they're literally superimposed. What if your network is really bad, right? If network is really bad, you can see your discriminator loss initially is bad, then becomes very good, right? Because it is quickly able to learn that, oh, green and the red, so green and the black are not the same. But as you slowly learn, so there's, for all these data points where it is clearly able to tell apart between these two, this value is much higher than random chance 0.5, and here it is much lower than random chance because it is able to tell apart between these two, right? So this is what a perfect gain loss looks like, and this is what type of learning is happening. And again, this is easy to explain in lower dimensions like this, much harder to imagine it in higher dimensions. Okay, now the other thing which I said is, if these networks are stuck, they need gradients to learn, right? And if they're not getting the gradients, they are not going to be learning. Or in other ways, if the gradients are never, because you don't have to have some magnitude, and you need to have, oh, you overshot by a lot or by a little bit, because if you are only generating, say your generator part is really bad, right? That is, if I pass in this random noise, what comes out is still like close to random noise. So you can see, if I'm trying to get a gradient between random noise versus a real cat, it's going to be so sharp. It's almost like saying, yes, you played a game of chess with Magnus Carlsen and you lost, right? Doesn't matter how many games you play with Magnus Carlsen, you're not going to be able to improve your chess by playing with him. You want to be able to play with somebody where you're like close to winning, so you know what things you're doing right, and you can learn, and you know what things you're doing wrong. So there is all these finicky things are there. It's so prevalent that it's one of the common things in the world, where people initially, when people get introduced to GANs, their images are terrible, and they just lose faith in GANs being able to generate them. And therefore, training or stability of GAN is a really well-studied, thoroughly researched topic. Not that we have clear solutions, but now at least we have better techniques. So if you use like Wasserstein GAN, if you use progressive GANs, these things will overcome these problems without you having to worry about it. But still, sometimes you might get stuck in these problems. Right. And, sometimes, GANs, all the examples which you look at, because see, there's no quantitative measurement, right? How good a GAN is. With classifier, you have this ImageNet competition where you can look at it and you can tell, oh, 87%, 82%. But with these, there's no real way to compare my GAN versus your GAN, right? Other than to look at a bunch of images. And people will only pick the best image from their runs and will give you the sample images. They will hide away all the bad examples, and you might not even get to it. So there's some selection problem. Second, it turns out as you start making the size larger, the amount of complexity that you have to add increases, and then the network then suddenly gets terrible. Like it starts making these Frankenstein type of stuff where it doesn't have this idea that, oh, because a dog-like feature, it might think, oh, the more feature of dog, the even the better. So it'll just start adding 6 eyes for 7 legs, because image is so big that it has lost this spatial connectivity and integrity of object. So these are the kind of the problems that with GAN. But now people, so for a long time, people were stuck trying to make GANs that can make larger outputs. But one breakthrough that happened was to realize you shouldn't do this in a single step. That's trying to go from a small Z vector to a very large image. You should make a smaller image that is already able to fool a network, then use that small image as the input to another generator that produces slightly bigger output, and that is able to fool the network, then make another. So you have multi-step generative process, and that is what is called as progressive GAN. Okay, now let's take a break from all the theory and let's look at some cool demos, cool examples. So one example is called as interactive GAN, where now you just provide some loose guidance to the network, and the network just imagines these are like your exemplars and tries to fill in the rest. So you can just do this green, and this is it's only trained on landscape, so it's always going to produce landscape, but you can change a little bit by changing some of these characteristics, right? So you can think of how like a Z vector is being manipulated with these inputs, and therefore you have this consistent output, right? Where you always get a mountain when you do this, right? So this is what is called as interactive GAN. And let's look at this video. It plays. I will not switch on the video, but here you can see, and this is very interesting since it is not a single step. You can keep changing, keep editing, and you can keep making it. And I think there is an online link somewhere where you can play. I don't know if it is still active, but it used to be where you can actually play with this and make your own. So I'll definitely encourage you guys to try that. Okay. Like what is this? Oops. Okay. This is, oh, it's so hard to use a cursor while you're in this format. So here, again, it is something similar where now you can, make small changes. And now question is, what is happening, right? Each time you're clicking some button. So here, the user is like trying to add some here, right? So he just takes the cursor and takes the black color and clicks it here. And instead of just leaving the one single black, the network actually adds more here. Why? Because it knows how to move in the manifold, right? That is, every output is a realistic image, right? So a face with one black dot is not realistic, right? But if it has one black dot here, and if it covers the rest of it with more black and makes it look like a hair, it is now a realistic image. So each time you try to take it away from the manifold, a point further away, it pulls you to the closest point in the manifold, right? And that is what is happening here. That is, each change you do, it is trying to fit it to be realistic image. And of course, it is not that good. But again, these are a few years old. The newer ones, which are heavier to run, but are better quality. But at least you can see even a small change actually produces a lot of change, because all that change has to make the image fool a discriminator, right? So all these images that are produced are the ones that can easily be fooled against a discriminator. And similarly, people have tried where now you can give this textual input. So Z vector is somehow being interacted with these text vectors, similar to your assignment 2 with the captions. And now that is used to basically make an image that is realistic. And this is basically your precursor to DALL-E. And DALL-E uses something similar. Actually, it uses Fusion. We'll talk later. But you can see how these input change Z, and when you change the Z, you change the image, right? But between, like for example, body is red and brown in color. So somehow, there is part of the Z that picks for red and brown, and And as long as you have this word red and brown, it'll always make bars with red and brown, even though other variables in Z are changing, some variables aren't, right? And therefore you're always getting red and brown. So this is very cool. Again, there's this more thing called as plug and play GANs, where it is trained on one type of data, and then you just expose it to different types. So from volcano, it is learning about mountains. From mountains, is learning about volcanoes. Definitely give this a try. The links are all down there. Now here again, you can see more different type of stuff that it can learn and can plug and play. That is, can take this one concept and apply it to different type of image and try to do a merger concept. But more practical use cases are in image manipulation or restoration, especially like, for example, if you have some, let's say there's a blackout here, right? For some reason while saving, something happened. So now if you use this as an input, remember, so at this point we are all talking about conditional GAN, right? Conditional GAN in the sense is not pure generative, because you are restricting some of the output of the GAN, right? That is some, it has to match overall this style. So hopefully in this in painting, no pixel other than these center pixels change, but we'll allow it to change a little bit if it has to make the image realistic. But we hope it doesn't look very different, especially the parts that are not occluded. And you can see, and so if you pass this image and if you ask the GAN to fill the rest, as a conditional input, what it fills, doesn't have to match with whatever reality was, right? Because there can always be multiple possible realities. These are all faces, right? So now, in some cases, turns out there's only one way to fill in, and in those cases, you'll get perfectly right. And there are cases where maybe there's different ways to fill that in, and it will try to do, different examples, outputs. One real world application of GANs is actually in super resolution, because oftentimes, in medical data or for some reason, images are stored at a lower storage space, so they are, heavily compressed, so they lose the resolution. So if this were, like for example, for some given image, like this is the original image. If you make it smaller, and now if you use some other technique like simply bicubic, which is what your browser uses, if you zoom on a smaller image, you'll get a an image that is blurry like this, right? Because there's not enough dense information. But then there are other techniques which are not GAN based. They produce images like this, which is good, much better than standard. But if you use GANs, what it produces, to me, it looks like very close to reality. Look at the water parts here, right? It's not able to fill in the details. It's still kind of blurry. Only face it filled a lot because probably testing a lot of faces, but other parts is still kind of blurry. But for GAN-based super resolution, everything seems to be upscaled. And remember, anytime when you look at a paper, look at a result, keep in mind that these are cherry-picked examples. These are the best examples, right? But that is same for everybody. Everybody picks the best example. So among the best example, you compare the techniques and you see which one you like. Similarly, you can, the deocclusion is similar to the one which you saw before, but now in this case, probably it is some natural occlusion, which is also possible in realistic in real images, and we just try to remove them, right? And you can see how network is able to do that. So you can see this is real. This sorry, this is the real. This is the generated image. This is occlusion that was added, and even it can remove specs. It can add specs. So it can do whatever you want it to do, as long as you have ability to measure these things on and somehow change the latent vector to impact this, right? Now the other use of GANs, conditional GANs, are doing this image to image translation, right? So going from, so remember we talked about sequence to sequence models, right? In last week, where it's going from text to text, whereas but somehow the modality of the text is changing. It's going from English to German. Here, image to image translation or pix to pix, or tensor to tensor, or transformer to transformer, they're all the same thing, where data is going from similar size in terms of dimension, but somehow the modality or its meaning is changing. In this case, is going from map to satellite. And now you might say, how did it know that this building was white color? It didn't know. It doesn't know that. it can fill it in whatever it wants. But as long as it looks like a realistic filling of a map of a street, this kind of a real photo to map, satellite map, it's accepted. Similarly, you can, now, I mean, going from this to this might seem like easier problem, right? Because it has to fill in less details. But sometimes, even that is tricky because you have to have, nice boundaries, right? Of, these kind of stuff. But going from this to this definitely seems very hard, and people have been able to use this. Similarly, going from, like the facade of the house to the actual, photo of it, right? So if you only give this where, blue and all that is just, types of the things, right? Like pillars or windows or parts of the house, it is able to make something that looks realistic. And these all are, very well-known data sets. So if you want, you can play with these data sets. The other cool thing, which actually now already is in some of the phones, is it can do, it can add lightning, or it can add, different context. For example, photo taken in the day, it can make it look like night. How does it know what night photo looks like? Because it has seen a lot of night photographs. Now, again, in reality, the training of this image to image is slightly different. But if you understand the process of GANs, you should be able to look it up. There are a lot of good videos, good blogs, but definitely, just go to YouTube and type, image to image translation and see how it works. But, under hood, it's just a GAN, it's a conditional GAN. So there's some input and trying to make output, but trying to keep some other things similar, right? So in this case, we are trying to say, okay, can we not change the pixels that is not occluded? So you will add that as a part of the loss, right? So model is trying to improve this part of the image without trying to change the other part. But then if changing other part makes it look Frankenstein, it might change a little bit, but it'll bear the penalty of changing that by making the image to be overall more realistic. Okay, and there's this website where you have all these amazing tools. You can. I mean, I'm really terrible at making CAD images, but if you are, I'm so glad that actually, here, let me see if I can make the image look. See, I added a cross here and made it made it look blind. So hard to do this. Okay, let's see if I do this. Oh, see, now this whisker is too big, so probably it failed. Maybe it'll work now. Let's try. Okay, you guys should give it a try. But there are other different, all these different types. We can play with it and see what it does. Okay. And the other other type which is similar to image translation, but it's a typical model, a typical structure. It's called a cycle GAN, and it's really popular because it has found widespread application in many different domains, especially in healthcare, where you have somehow this two different modalities like MRI, CT. So here, the big idea was, if you're trying to take this and trying to make an image like this, it's also a good idea to go one step further and say, what would happen if I were to take this as input now and try to make an image like this? So you have this cycle consistency. There's not only going from A to B, but also going from B to A. So, overall, the idea is very simple, right? You have this cycle consistency, and just doing that allowed people to make GANs that are much better, qualitatively speaking. The result is more realistic. Like, for example, Yosemite is going from summer to summer to winter, and winter to summer. It is, you can see, it doesn't do perfect job. There's still some snow left, but it is able to do a good enough job that like, for example, there's a nice GIF of horse to zebra, and of course somebody has trained this, and it could fail because these things are really not designed to do everything well. So unless you have a good segmentation model, it might just segment everything because it thinks all of it is part of, because this network doesn't really understand the delineation of the object. So there are limitations of all these techniques. Okay, let's see how many more examples. And then their videos are all actually slightly harder to do, because now you need to have a temporal consistency also, right? Every frame has to match. So, but people have tried similar ideas, more layers, more loss. It's okay, but video GANs are not that good. So, but but I think we'll get there. Now the other thing is, again, style transfer. Now the original style transfer didn't use GANs, but the newer ones, they definitely use GANs and they do much better job. I think they, Gattis et al. Is like the original style transfer paper. And in this particular photo with this style, you can see the ones using a GAN does better job than the ones not using the GANs, right? And similarly here, different styles has been transferred. And now, like I said, you can also manipulate the attributes, right? So, and there's this nice paper called as Infogan. So look it up, where Infogan teaches you what if you knew these attributes. So say, for all my photos, I knew if they were wearing glasses or not, if they have hair or not, what is the color of the hair. So say I have these attributes, right? So what I can do is, let me see if I can. I will, let me just annotate on the screen itself. So say I have, so, what does my Z vector look like? So my Z vector looks like, a bunch of numbers, right? So say I have a Z vector of size 100. When I say size 100, the dimensions are 100, right? So remember, all of the values in the Z are randomly sampled. We don't know any value of the Z a priori, right? And say, the images in my data set, they have 10 attributes, right? One of the attributes is hair color, one attribute is glasses, one attribute is gender, one attribute is, ethnicity, and all that sort of stuff. So if I have 10 attributes, what if during training, I consider my Z to be of size 110, right? That is, the first 100 numbers are coming from here, and the remaining 10 numbers are coming from here. So each time I sample, you can see the 100 numbers are really random, but the other 10 numbers are not random, and they are consistently same. So for say, if the fourth digit, so I'll have a vector of 10 here, right? Of which, say, the fourth digit is a binary value of, let's say, 1 or 0, depending on whether they're wearing glasses or not, or they're not wearing glasses. So each time during training, if there is a person wearing glasses, this vector will have 1, and if they don't have glasses, the vector will be 0. So now if you train again, and during inference, remember, so during inference, you're going to have to sample a new random number, right? I will sample a new 100 one, but the other 10, I will add it based on my own liking, right? So I will take this 100, I will have the other variables, except now for glasses, I will say, yes, make them with glasses. So now I can always make people with glasses. But the same people, now I can just keep everything same, except I will change this variable. And now I will have, the same person without the glasses, right? So you can see how you can, learn all these attributes. So, like software depends on what attributes you have. So this is where we are, no longer strictly in unsupervised learning. We are using some labels, but these labels are able to give us a lot more value in our image generation, right? Because when we started talking about GANs and this latent vector, we didn't realize that we could directly map individual z dimension vectors, z dimensions to individual features. But I remember, I'm definitely hiding a lot of detail. This is a simplification. This is one of the really well-written but dense paper called as Infogan. So if you really want to know how this happens, you should check out Infogan. So there is, I'm definitely making it sound simpler than it is. But overall, this is the idea, right? So if you have these attributes, you can take advantage of it. Okay. Let me clear this. Oh, come on. Okay, and so this I told you about progressive GANs, right? This is the only type of GAN which allowed people to make much larger size output, where you first make you start with a random Z, make a like 64 by 64, use that as a conditional GAN input. You use that as input to make 256 by 256, then go to 1024. And as you can see here, now faces are bigger in resolution, compared to what we were seeing before of like 30 by 32 by 32. So when this came out, it was a really big deal, right? Now a couple years ago, now this was a few years ago, Now, looking back, these images are still nowhere close to the quality of what you get these days with, this person doesn't exist, right? But all those advancements came later on. This was a big deal when people were able to make images this size. Okay. Now, just very quickly, because this definitely gets a little bit, more hairy, but overall, I told you about GANs to make, as a generative process. You can make more images, you can get more of the data, right? You're learning the joint distribution. So are GANs the only way? No, because if you remember when we learned the autoencoders in the first week, autoencoders can also do, and it turns out there is a slight different variation of this autoencoders called as variational autoencoder, where the decoder, instead of the parameters directly being encoding, these are the parameters to a distribution, so that during inference time you can sample them more. These are called VAE. If you're interested, you should look it up. They are also able to produce images, but only turns out that compared to GANs, they are not very sharp, because VAEs typically minimize mean square error. So they are always, if you have mean square error, it's best to be around the mean. So more blurry images have overall less mean, and therefore, they are lower loss, and therefore they don't make as sharp images. But if your data is not images, and if you don't mind it to be closer to the mean, it's all right to use VAE. Similarly, there's the flow-based models, which are very complicated, but you learn some function that does the flow of each pixel, definitely beyond the scope of this. And but the other type, which is making a lot of noise these days, are called as diffusion models, and this is what I think DALL-E, DALL-E, DALL-E uses. And the idea of the diffusion model is kind of similar with GANs, with the Z and with the progressive GANs. But I told you that, what if you start with pure noise, and then you make an image which is lower dimension, then you make another image. But in diffusion model, right, the idea is even simpler, right? You start with your data point X, right, and you add noise to the process, right? So remember, here it's actually going from right to left, not left to right, and you will see later on why. So you start with a data point, and you slowly add, for each point you add some some Gaussian sample noise. And if you keep adding noise to every point, eventually the whole thing becomes like a blob of a noise, like a multivariate Gaussian noise. So at final infinity, all images will look like this. But each step you add a little bit more. Now, question is, what is happening in each step, right? So in each step, you're also learning a reverse process. That is, you're learning a process that goes from this level of noise to this, right? So you're starting from a clean image. So it should be possible to learn to go from this to this, right? Oh, just remove these noise. Then it should be possible to learn to remove this from this. So, and remember, this is almost like a Markov process, and that's how it's implemented, right? So you do one step at a time. Now, during inference, you just have to run the inverse process. And now, you may say, but wait a second, what is this? What does it mean to learn go from noise this? You are basically, so whenever, this is where the first slide where I said neural network is nothing but a function, right? But yes, it has parameters, it's parameterized function, but it is a function. So here I'm just this arrow represents a neural network. It could be 1 layer of MLP, 10 layers of MLP. Different depends on implementation, depends on how much data you have. But say you have a bunch of data and you have a big network which just learns to because remember, you have the input, you have the output, so you can train this network, right? You can do you have the correct output, you produce some output, do the error, mean square error, whatever loss you can do this, but you can learn this p theta xt minus 1 given xt, right? So now so during inference time, you start from some random noise, right? Go to next step, go to next step, go to next step. Eventually, you'll produce these images. And by the way, I definitely didn't do enough justice, but I'll encourage you to look at this tutorial, which is really nicely written, or this video, which explains you the process one by one. What does the forward process look like, the backward process, the math behind it. But if you're really interested in learning the details of this new DALL-E generation methods, diffusion models is the way to go. Now, for a long time, people knew diffusion as a process, but they didn't really think it could scale up to make such good images, but turns out it can. So if you're interested, you should look it up. Yeah. So, I mean, that's all I have for today. I know we are a little bit over time, but, I will wait. If you have more questions, please feel free to ask. And if you want to ask privately, that's also fine by me. I'm happy to, wait until the end of when everybody has left. So ask your questions, or if you want me to stay longer, just send me a message on Zoom chat, and I'll stay longer.
I apologize if this is something you covered at the beginning when I was getting the capacitor, but as far as the homework, what are we looking at for a due date? And I don't know if you already went over some homework questions at the beginning, but if you did, I can wait until this video is posted and take a look. But
No, so I didn't go over any homework questions. I can tell you the due date. What was the due date I added on the channel? Here you go, sorry. So, my due date, suggested due date is 16th August. I think that should be plenty of time to submit the assignment to, and hard deadline is 23rd August. I think at that time, I will also have to, start grading all the assignments and start giving the scores to the university. So hard deadline is 23rd. So, but definitely try to do it before. The only thing I told about the assignment earlier on is if you have not started, definitely start now, because there could be few kinks that you'll have to figure out before you are in a place where you can at least get some output, right? So definitely start now. But if you are stuck, say you are stuck with the homework, you have no idea. So you have image embeddings, and you have your image embeddings, right? Sorry, image embeddings and the caption embeddings. So the easiest would be to generate all your embeddings, do a PCA, reduce it down to lower dimension. You can even go down to 2 or 3 dimensions, PCA or UMAP, and now you can start actually visualizing. If it's a 2D plot, you can now plot where all my images are, where all the captions are, and you can even do k nearest neighbor, or you can do some kind of a similarity, or just cosine. So I think that's the easiest way to go. But if you want to be more clever, you can then you can, because I've not stopped you from doing anything more or different than what I've suggested, right? Maybe using a existing captioning based model to get a new caption on the provided images, and now comparing new provided caption and the caption that I have given you to find if they are closer. Maybe it is easier to do distance matching between caption between text vectors and text vectors versus text vector and image vectors, right? And if you really want to, because the purpose of the assignment is for you to learn, right? So if you really want to learn object detection, this is your best opportunity. You can run. There's plenty of amazing libraries, and I think Hugging Face already has all these things. So you can give an image, and you can ask it to detect everything that image has. So you'll get a name of everything and their location. You don't care about location, just get a name of everything. And now you have a bunch of words, and they have a caption. So any caption that matches most of these words, like a TF-IDF, because you don't want to match words like the, is, of. So you can even start doing those, right? So there's plenty of ideas abound, and I would love to see you guys be creative, but definitely believe that each image has did I tell you exactly how many? Okay, I'll just say multiple. Each image has multiple captions that humans wrote, so it has to be meaningful. It'll make sense. If they're really far off, probably you haven't done it well. And especially if you do, take a high dimension thing, and if you try to reduce to a smaller one, you have to be careful, because sometimes you might, you might squeeze the data in different dimensions. You can average them, so that even if there is a signal, that signal has been averaged out because you went from high dimension to lower.
So I had a couple of questions, because I took what you provided and I was kind of basing it from there. So I'm able to get the features from all of the captions, right? But the first question is how do you load in like a set of images
Where do you want to load?
I'm sorry, what?
So you said, how do we load in? So where do you want to load, right? Do you want to send a set of images to the model so that you can get the features back?
Sure. Yeah. So like in the example, you just had one like JPEG and you just called it by its name. How would you do that programmatically for the 500 or whatever images?
Okay, let me quickly open that collab. I will show you because first of all, remember, okay, let me share my screen. Okay, so you can see this screen, right? So
Yep.
here, right? So here, okay, this image is still a single image, right?
Mhm.
Now, if you see, okay, let me just run. So by the way, you should, if you connect here, you'll get a free GPU that should be able to run, who knows, 100, 200 images at a time, depends on the size of the model. Okay, let's see if we can quickly run this, because I want to be able to run up to here, and I want to show you something. So if you see the shape of the X right now, it is, shape of one image, right? This image has a height, width, and channels, right?
Right.
The reason we do this, right? Because what happens when I do this? Now, when I do this, if you see the shape, now suddenly we have an extra dimension, right? Because all these models, all these functions, they are actually designed to take a batch of images. They're not designed to take a single image, right? Here, so now, so say you have, so you have loaded 10 different images, right? So let's say, I'll call images. And, for the sake of simplicity, I'm just saying that, I have 10 images in a list. Now, if you see, images is actually an array, right? Length of images. So I have 10 images, and images 0 has a shape of a single image. So if you have image on a list, right? If you simply
Mhm.
do images as mp.array images, let me call this images array. Now this has the shape of see, this is the problem, right? Because images was we already expanded the dimension, right? I didn't want it to expand the dimension. I want to go from here. But let's do this again. I don't want to expand the dimension. I want to do this. So now if I do image the shape, that's perfect. So now if I do this, so now if you see, now basically I have 10 images, right?
Mhm.
And now if I were to pass and if I were to do this, see, it is going to take some time, right? Because now it's going to run all 10 images, right? So,
Sure.
but if you do this, you can see here how now I got the feature for all the 10 images in one shot, right? So if for the image one, this is your image one, this is your image two, and so on and so forth.
Sure. I guess what I'm not understanding is, so if you could scroll back up just a touch, a little bit higher. Okay, so cell 13. So you specify that image path is example.jpg.
I see.
Um,
So, okay.
I want to give it a directory of images. How do I do the
Perfect.
directory?
Yeah. Let's see. So does image, so this image is, so that depends on what library you are using. So we are using Keras pre-processing image, right? Because now let's look at this function, because it's possible. Keras load multiple images. Let's see, Keras load multiple images. There must be way, but I mean, that optimization is, to be honest, not worthwhile, because it is going to take the same time. So for example, if I have a bunch of images here, let's say, let me do this. Yeah, let me do. Oh, actually, I have sample folder. Okay, so say all these are my images. Right? Or you know what? Let me do this. Dir images folder, and now C touch images folder. Let's just say we have these images. Okay, and so if I have this folder called as images folder, you can see this has all these images, right? So the best thing, so easiest way with in the way I do it, yeah, right? So I do it so this is one of the built-in Python functions, right? Now if you do for f in glob, and now you can just basically give your directory. You can say images underscore folder asterisk. So asterisk will go over all the images. If you know it is JPEG, you can do this, right? So if I do this, and if I do printf, you can see here it will basically loop over all the images. So I will, if I had to load all of the images, I will do this, and I will basically do images dot append, and whatever function was there to load. To be honest, I'll do it like this, right? Whatever is the file here. So now this way, I have an array that has all the images loaded, because there will be no actual advantage of doing them in a bulk, because reading from disk is going to be sequential. However, there might be, that for Keras might already have what is the function using? Pre-processing images. Okay. Pre-processing. Let's look at, because often it's a good idea to look at the library to see what functions it actually has, right? So load image function, image data set from directory, right? So you see there is a function called as image data set from directory. Probably it might, so if you give a directory, it might probably read all the images in directory. So probably, it's best to use this. But who knows, maybe there are more things that it needs. So load images, loads a single image. Image to okay, so there's only, probably this is the function I'm looking for. I have not used it, right? And it looks like it does a lot more stuff than what we want, but definitely learn it, because this is a good opportunity to learn, because in the future you might have to like simply truncate the size, or may have a different batch size. That way, if you use these functions, and say if you want to actually pass in an image that is bigger output than the original size, then you can give the interpolation function, right? You can do that. But if you only really wanted to load images one by one, I'll just do this, and now I have the images array, and then rest how to do.
Sure. And then if I can, I think I'll just ping you on Slack when I've got my other question to